Let's take a closer look now at the nuclear binding energy. This is related to nuclear stability. Okay, so the nuclear binding energy is defined as the energy required to break up a nucleus into its component protons and neutrons, its nucleons. All right, one thing that's interesting though, when we look at the mass of a nucleus of an atom, we always find that the mass of the nucleus is less than the sum of the masses of the individual nucleons. What do we mean by that? Well, we'll take a look at this. Let's look at the fluorine-19 nucleus. Well, it's fluorine-19. We can see it consists of 9 protons, and the mass number is 19, so that must be 10 neutrons. 9 protons, 10 neutrons. Well, we have the masses of protons and neutrons. They're known pretty well. And so the mass of a proton is 1.007825 AMU. Mass of a neutron is 1.008665 AMU. Recall the mass of a neutron is a little bit larger than the mass of a proton. All right, so if we have 9 protons, 9 times this number plus 10 times this number, then we add together the masses of the protons and the neutrons in the nucleus of fluorine-19. We get 19.15708 AMU. That's how much a fluorine-19 nucleus should weigh, because 19.15708 AMU is the mass of 9 protons plus 10 neutrons. However, the actual measured mass of the fluorine-19 nucleus is 18.9984, a difference of 0.1584 AMU. The mass of the fluorine-19 nucleus is 0.16 AMU lighter than the mass you would predict it would be by adding up the protons and the neutrons. All right. This difference in mass, and turns out this is all nuclei are a little bit lighter than they should be. This is known as the mass defect. Well, where did the mass go? Turns out when the fluorine-19 nucleus came into being, that mass was lost as energy, lost as heat given off to the surroundings. All right. That means that the formation of fluorine-19 is an exothermic reaction, because when it is formed, heat is given off to the surroundings. And it turns out this mass was converted into energy in the form of heat, and it follows Einstein's famous equation E equals mc squared, or delta E equals delta mc squared. The amount of energy that is given off is going to equal to the change in the mass. All right. So for fluorine-19, delta M for this equation is, or delta M here, is negative 0.1587 AMU. Well, how much energy is this? Well, let's recall, E is energy, delta M is a change in mass, C is the speed of light, and we have to square that. Here's just some things in order to do the calculation, which you will not have to do on the exam. I'm not going to make you do this calculation. I just want you to see where these numbers come from. We know 1 AMU is 1/12 the mass of a carbon-12. 1 carbon-12 is 12 grams per mole. So if you had 1 kilogram, it turns out that would have a mass of 6.02 times 10 to the 26 AMU, because 1 gram or 1 gram per mole would be 6.022 times 10 to the 23rd. And so a kilogram is 1,000 times that. And also this definition, 1 joule is 1 kilogram meter squared per second squared, when you convert joule into SI units. So plugging in our numbers, delta E equals our mass defect in AMU. We change it to kilograms via Avogadro's number times 1,000. 3 times 10 to the 8th meters per second squared. We got the speed of light squared. And then we know that 1 joule is 1 joule per every 1 kilogram meter squared per second squared for our units. And we come up with the change in energy when a fluorine-19 nucleus is formed from 9 protons and 10 neutrons. The mass of that nucleus is lighter, has less mass than the 9 protons, 10 neutrons. That defect in mass means when a fluorine-19 nucleus is formed, that process gives off 2.37 times 10 to the minus 11th joules for every nucleus. All right. So if I had 1 mole of fluorine 19, if I made 1 mole of fluorine 19 from its protons and neutrons, it would give off, negative sign means exothermic, it gives off 1.43 times 10 to the 10th kilojoules per mole. That's 14 billion kilojoules for every mole of fluorine 19 that gets made. Note, most chemical reactions are about 200 kilojoules per mole. So these nuclear reactions, making 1 mole of fluorine 19 from its protons and neutrons gives us 14 billion kilojoules of energy released, whereas most chemical reactions only 200 kilojoules of energy released. Okay, so when we continue on with this, now I want to compare, well, then how stable are other nuclei, because the amount of energy given off to form it tells us about how stable it is. But the problem is different nuclei have different numbers of protons and neutrons, so we need a nicer number here, and what we have come up with is a number that will compare with two different nuclei that have two different numbers of nuclei. We find the binding energy per nucleon. The nuclear binding energy is just the amount of energy given off, the stability of the nucleus due to the missing mass. And so what we're going to do here for fluorine 19, note it was 2.37 times 10 11th joules given off for the 19 nucleons, which gives us a nuclear binding energy of 1.25 times 10 to the negative 12 joules per nucleon. All right, and so then if we do a graph here of the nuclear binding energy per nucleon on this axis and the mass number on this axis, we find that hydrogen or deuterium is way down here. It's not on my little graph here, but helium would be right about up here. Helium is going to be right up here. And then we see that as we get heavier and heavier nuclei, the nuclear binding energy gets larger. Now, the nuclear binding energy is how much energy is given off. Therefore, larger amounts of energy are given off per nucleon as we get heavier and heavier nuclei. So that makes them more and more stable. So the higher you are on this chart here, the more stable the nucleus is. And what we find here is once we get up to iron, the stable isotope of iron, that iron 56 has 56 nucleons in it, 26 of which are protons, so that makes 30 neutrons. That's at the very apex of this curve. That's at the top of this curve. So when we go from hydrogen through the periodic table to iron, to iron, these nuclei get more and more stable. The nitrogen nucleus is a little more stable than the carbon, and so forth. There's some minor variance in here. Silicon is more stable. Chlorine is even more stable up till we get to iron. And the iron 56 nucleus is the most stable nucleus of any element, which means once we get to cobalt and nickel, these nuclei are a little bit less stable than iron. And the further we go down, the less and less stable the nuclei become. Iron is the most stable nucleus. And then as we go up to uranium-238 here, that will be the least stable of our naturally occurring nuclei, the things that we do find in the environment naturally. Recall, all of these guys here, neptunium, plutonium, americium, berkelium, we had to make these. So uranium is the heaviest naturally occurring nucleus. All right. So what holds these nuclei together? That would be the strong force. That's what bonds the nucleons together. The four fundamental forces are the strong force, the nuclear strong force, the weak nuclear force, the electromagnetic force, and gravity. Strong force here, it's not gravity, it's not electromagnetic, it's a strong force that holds the nucleons together, operates only within the nucleus. A few things about the strong force. Two tiny protons have an electrostatic repulsion of 50 pounds over a distance of only 1 times 10 to the minus 15th meters. They're very, very small, but they're full positive charges, so that's a pretty strong repulsion. 1 times 10 to the minus 15th meters is 1 femtometer. All right. This nuclear strong force is unaffected by mass or charge. It ignores electrons. It treats protons and neutrons as equals. It holds the proton to the neutron also. It's very repulsive at distances just under 10 to the minus 15th meters. If you got within the femtometer, the nuclear force would be very repulsive, but it's very attractive from 1 to 2 femtometers. And after you get about 2 femtometers away, 2 particles 2 femtometers away, it's practically zero force holding them together. By the way, 1 femtometer is approximately the radius of a proton and a neutron. So these are very small distances. All right, so that's a strong nuclear force that holds it together, and there's a whole lot of research in cosmology, in physics, to try to get all these forces, the 4 fundamental forces, to be a derivative of the same overall force, combined forces theories. All right. Let's take a closer look, though, at our nuclear reactions, because we're going to throw in a little bit of something. This next part really isn't going to be on the exam, but it's something you should know because you hear about it every once in a while on various science shows that we all watch all the time. All right. When we look at our nuclear reactions, for example, we have a neutron that decays in the proton. Recall we had to balance the top number and the bottom number, to get this to work. However, it turns out it's a little bit more complicated than that because we can divide all of our particles into classes. We have leptons and baryons. Leptons are called light ones. They're our lighter molecules, such as electron, the antiparticle part of the electron, the positron, and 2 new particles, the neutrino and the antineutrino. Now, a trino is a particle that, as far as we know, has no mass, has no charge, but it carries energy. What we have found is when we were looking at these reactions, when the nuclear physicists were looking at this reaction, they found, okay, this occurs and the energy is given off in form of this beta particle, but this beta particle isn't carrying enough energy off. When you look at the energy of the neutron and the energy of the proton and the electron that was given off, the beta particle, we found out there's not quite enough energy given off. So there was another particle called the neutrino that was put in, that was decided, okay, let's have this new part. There's got to be something carrying off this energy that's called neutrino. Here's its properties. But how do we know where is that mass? Where is this neutrino? And they decided, okay, let's divide everything into the light ones, the positive, or the light ones, the ones that don't have much mass, the electrons, beta particles, their antimatter counterpart, the positron, this neutrino particle we just came up with, and the antineutrino, its antimatter counterpart. So those are the leptons, the light ones. The baryons are the heavy ones, and those are our protons, neutrons, and their antimatter counterparts, the antiproton and the antineutron. Okay, leptons can transform into other leptons, and baryons can transform into other baryons, but you cannot change a baryon into a lepton, meaning a proton cannot become a beta particle. An electron, a neutron cannot turn into an electron or a positron. A proton can turn into a neutron. Well, we see that up here. Protons can turn into neutrons and vice versa, but the baryons cannot convert into leptons. What this means then is when we are balancing these equations, we really need to keep track of the lepton number and the baryon number. So when we've been balancing before, really we've been kind of looking mainly at the baryons, but we haven't looked at the leptons too much. Well, we define the lepton number of an electron or a beta particle as 1. The positron, the antimatter, is a -1. The neutrino gives a lepton number of 1, and antineutrino lepton number of -1. Note, Particles that have mass, or normal particles, have a lepton number of 1, antiparticles -1. Baryons, the particles, protons and neutrons have baryon numbers of 1. The antiproton, anti-neutron would have -1 as a lepton number. So we must conserve lepton numbers and baryon numbers in these nuclear reactions. So when we look at this, here's our neutron that converts into a proton plus our electron, our beta particle. When we look at the baryon numbers, well, the neutron is a plus 1 baryon. The proton is a plus 1 baryon. Electron's a lepton, so we don't worry about it. For our baryon number, we have 1 neutron plus 1 proton, 1 on this side, 1 on that side. They equal each other, we're good. But when we look at the leptons, neutron, that's a baryon, so there's no lepton on the reactant side here, but we have 1 lepton on the product side. We have this beta particle given off on the product side, which means we need another lepton to make this side equal this side. It turns out the way to do that is to, well, if there are no other leptons over here, the only thing that can be given off in a nuclear reaction is a neutrino. And so we realize if this is a plus 1 on here, and we need this side to equal 0, we need an antineutrino on the product side. So whenever a neutron decays into a proton plus a beta particle, it also releases an antineutrino. A little bit more energy is given off. Not mass, energy is given off in the form of an antineutrino. And its antineutrino we know is given off because our lepton numbers have to add together and the neutrinos are given off. They're not taken in. Okay. Note, so here we have electron capture. Here a proton captures an electron to become a neutron. Note our baryon numbers are going to work out. Proton is 1 and neutron is 1, but our lepton numbers don't work out again. We've captured this electron here, which gives us a 1, but what else has to be given off on this side? Well, if we have 1 lepton here, we need a 1 over here, so whatever's given off has to have no mass, but have a lepton number of 1. That would be just a regular old neutrino. So, what we have found is when neutrons get converted into protons, they give off beta particles and antineutrinos. When a proton undergoes electron capture to form a neutron, it gives off a neutrino. Okay. Just so you know, this is why we have neutrinos, and I'm not going to ask you to put in the neutrinos. I don't know, I might get a little crazy. But this is the deal with where neutrinos come from and how do you know if it's a regular neutrino and an antineutrino. Note the interconversions of protons and neutrons are governed by the weak force. Note, you're not expelling a proton from the nucleus, you're just converting it, and that's the weak nuclear force. All right. And finally then, this video question. Does a neutron contain a proton, an electron, and an antineutrino? Because when you think about chemistry, when you look at this reaction, it looks like a neutron. We start with a neutron, and it gave off a proton, an electron, and an antineutrino. So is a neutron a combination of these 3 things? No. A neutron is not a proton. A neutron is not a proton and an electron and an antineutrino all balled up together. A neutron is its own particle. It's just when it converts itself into a proton, these 2 other particles are made. A electron beta particle is made and it's given off. An antineutrino is made and it is given off. But there was no original antineutrino just sitting in here. All right. These nucleons, protons and neutrons, are actually made of more fundamental particles called quarks. And when quarks rearrange, they form and give off the beta particles and the neutrinos. All right, so that's it for this section. We will continue on by looking at how we can get energy from nuclear reactions, the good and the bad.